All right, so we've got a 7-segment display. And what it is it's 7 LEDs that are put into a pattern in which we can get numbers and a few letters out of. Okay? All they are LEDs, and either they've got their cathode or their anode tied together. And so if I want to turn this segment on right here, I just, put power through that LED. Okay? So I definitely want you to have something that looks like this. I think this is the best way to do it. For me, it is, at least, right? Let me double check that that's right. Yeah, goes clockwise, and then the G is in the middle. Okay. All right, we're going to talk about one main thing today, but I'm going to tell you a little bit about it. We've got two things called encoding and decoding. Encoding is something when we take something we understand and put it into a form that something else understands. Say the microprocessor understands. Okay. Decoding is taking something that the microprocessor understands and changing it into something that we understand. Okay. So this is encoding. This is decoding. It's a micro P for microprocessor. Okay. Now, it doesn't matter what scheme you use to encode something. It really doesn't. It's not black magic. There's not anything that says 0001 is equal to 1, right? Now, when I tell you binary representation 0001 equals 1, like if we're encoding numbers, that 0001 could represent a 1, okay? So it's important to not only know the information that's in, either you're encoding or decoding, but you need to keep track of how you're doing it back and forth, okay? Because what does what is 0101? It's a 2 in binary, but if I don't tell you what I encoded it for, that could be, it could be, it could be a word. I could have a dictionary, and I could encode this sentence. I could say, the house is blue. And then I could say that this was going to be 001, this would be 010, this would be 011, and this would be 100. No rhyme or reason. Okay? And then all you need to know is what I used to encode it. So you've got imagine you've got a decoder, right? And the information, boom. So if you know what I used to encode it, and then you've got you've got the ones and zeros, then you can decode it. Okay. So what we're going to do is we're going to take we're going to take 0, 0, 0, 0 and not do anything with it. We're going to take 0, 0, 0, 1, and we're going to say that that represents an R, a lowercase r. Okay? Then we're going to say 0, 0, 1, 0 is going to represent a lowercase o. All right? And then we're going to say that 0, 0, 1, 1 is going to represent a lowercase b. Okay? And then we're going to skip 0, 1, 0, 0. And then we're going to say that 1, 0, 1, 0, 1 is going to represent that lowercase b again. So we're going to get, a cool old school Rob B, right? Actually, let's make that right there represent a hyphen. Okay? All right, so we've got A, B, C, D, E, F, G. All right, up until this point, you've been dealing with one thing happening at a particular time. Okay, like we made what was called a binary to decimal decoder. Like if we wanted an LED to represent 0, so we have an LED over here that is representing 0. We've got it like right next to something that's written 0, right? We could, make code that would take that 0, 0, 0, 0, convert it to 1, 1, 1, 1, and turn it on only when all of those inputs are 0, right? I could take an LED and say that it represented 7, right? And then I would take, what is 7? It is 0, 1, 1, 1, right? So I need to invert that first one because it's a 0, and then 1, 1, 1. So 0, 1, 1, 1 would let this turn on. And so I could have one LED that represents 7. All right, so we made a decoder before, like when we had it just so that LEDs would turn on in succession. Okay. But now we want it to be a little bit more complicated because it makes it a little bit more fun. And we start to see things for what they are because it's just a variation of a theme. It's always just a variation of a theme. We've got all of our tools in our tool bag. We're about to be able to count. We're about to be able to add, subtract, multiply, divide with just the tools that we've got. We don't have any extra tools right now, and we're about to make it say Rob B. Okay? So what we need to do is, the easiest way to do it is instead of like drawing out, a convoluted whatever, right? We need to start looking at when things are true. Okay? When is A on? It's never on, is it? No. So it's never on. When is B on? It's never on again, right? It's never on. Like for what we want to do, the B segment is never turned on, right? What about C? O, B, whenever O and B are on, right? Like whenever we want to make a lowercase o or a lowercase b, right? So what can we say? We can say when it's 0, 0, 1, 0, 0, 0, 1, 1, and 0, 1, 0, 1. Those are the cases that it's going to be on, right? Oh, wait. For C, right? For this segment right here, it's on right here, and right here. See, we're making an O, like a lowercase o. So that C, this is the C right here. It's on for O, B, and B. Okay? So those 3 times it's going to be on. Okay? What about D? It's on for O, so 0, 0, 1, 0. It's on for B, 0, 0, 1, 1. It's on for the other B, 0, 1, 0, 1. Now, do y'all notice anything that C and D are on at the same time? Okay, so that might help us make this circuit a little bit simpler. Yeah, same. If C's on, D's on. What about E? Not quite. Like this segment right here, and then I look at my letters. R, right? O, lowercase o. B, hyphen B. Okay? So look at this segment right here. Look at the E segment. And it is on for R. So 0, 0, 0, 1. It is on for O. So 0, 0, 1, 0. It is on for the first B, which is 0, 0, 1, 1. It is on for the second B, which is 0, 1, 0, 1.
Figuring out which letter represents what. I guess that's what I was confused about. Is like, you get what I'm trying to
Like up here?
like, yeah, like how are you going about figuring out which one lines up with?
That this right here. Like, so let me do something real quick. All right, so I want a lowercase r. So I'm going to need a G and an E. Okay?
Oh, okay.
I want a lowercase o, so I need a G, D, C, and E. I want a B, so I need all of those with an F. Is that better? All right. Now I'm making this up, right? Like I want this 7-segment display to say my name. So I'm going to have to encode the information the way I want it to so that I can decode it. Is this starting to open up? Like y'all starting to see that like now those 1s and 0s aren't just numbers, they're letters, they're pictures, they're anything, right? Okay, So E, 1, 2, 3, 4. Yeah, it's on 4 times, right? F. When is F on? F is on for just the 2 B's, right? 0, 0, 1, 1 and 0, 1, 0, 1. And G is on for practically all of them. It's not on for 0, 0, 0, 0, but it is on for 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1. Now, if I wanted more steps in this, right? I could go to all right, 0, 1, 0, 1 in binary is 5, right? I could go 6 and 7 and still get it done with 3 bits, right? I could have 2 other things that are done after this and get it done with 3 bits, right? Like this size right here. Do I even need these zeros over here? No. Now, if I want it to go ROB-B and then wait a long time until it starts back over at 0, right? I could encode that extra bit. But what'll happen is, even though I've got a 4-bit counter, it'll count up to 7, and then whenever it goes to 8, it'll be 1, 0, 0, 0. And if I'm only paying attention to those 3 bits, it'll start back over with ROB-B. Okay? So we're going to ignore these bits right here. Okay? We're just going to do 3 bits because that's all we really need. Cool?
Now, would that just work for being the first? Like, say all the zeros were at the last place.
Yeah, it wouldn't work.
It just works for the first.
Yeah. Well, I mean, if we found something that like none of the C's mattered, we could get rid of that. But usually it's going to be your most significant bit that you could get away with, because like I just arbitrarily did 4 bits. I could have did 10 bits and like, you know, all but 3 of them were moving. Okay? All right. So how are we going to make a circuit that does this? Let's look at C real quick. We need it true when A naught, B, C naught. Y'all see that, right? Or A naught, B, C, or A, B naught, C. So that's going to be C equals, C and D actually equal that, right? And we'll just go through all of them and do this, okay? So, pull up our favorite program. I like Deeds. Do y'all like Deeds? I like Deeds. Me too. Oh, the one with the breadboard?
Yeah.
Oh, Tinkercad. All right, so let's just go ahead and let's put a clock in there. How a clock is made is an oscillator. And in other classes, you learn how to build an oscillator, okay? It just goes from 1 state to another. Okay. It's under input. Yeah. All right. We're going to take that and put it into a counter. So go to counter and then 4-bit up. Okay. Now we want to be able to give that a 0 right there. Like whenever it's got a line over it, it means it's inverted, right? In normal parlance, in normal stuff, if there's not a 0 right there or a line over that, that means that it's active high, that it will clear when it's high right there. Whenever it's got a inverter on it, that means that it is cleared whenever it's a 0 there. Okay. Now we have inputs that we could flip a switch. Okay. But we're just going to put a high level logic right there. Okay. We're just going to tie that to 1. Okay. So that's an input. We'll wire that up. We don't want too many things going wrong with this. Okay. Now I want to see the counter count. So I'm going to take an output LED array, a 4-bit LED array. I'm going to revolve it. And this is just so that I can see what number I'm on at a time. Okay.
So you put an input in there, and then
Yeah, I put for that 1, I put a high level logic 1, right? Under input. It's an output. Like, so it's a, man, my stuff is getting funky. Oh, I just got back from Siemens where, yeah.
wait, is your little level 1 thing rocking input your response?
Yeah. Well, I zoomed in pretty hard. All right. Before I go on, I'm going to test this. I'm going to save it, and we're going to say, we're going to call this Rob _ decode. I'm going to turn that clock on. It's not doing anything. So that 1 logic's not doing anything for that clear right there. So I'm going to change that to an input switch. I don't know why they put that logic 1 in there if it's not going to work. It didn't work last time I did it, but we have an updated version. I thought for sure that they would have fixed it by now. But that's why we're doing it as we put stuff in. All right, so we recognize that as counting up in binary now, right? We'll build a counter. All a counter is a divide by 2 circuit. If you look at that least significant bit, it goes on, off, on, off. And every 2 times it does on, off, the next one does on, off, on, off. And then divide by 2, the next one is doing on, off, on, off. All right, so we're about to have some fun. All right, so we'll stop this and let's go to output and go to 7 segment and do 1 digit unencoded. Okay. Now we've got A through G. And if we want to turn on the A at any time, we got it. Okay. Now, when is A on? Never on. When is B on? Never on. So we don't even deal with those. All right, let's make C real quick. C is on 0, 1, 0, 0, 1, 1, and 1, 0, 1. Okay, so I'll just take a 3 input AND gate. I'll take three input AND gates. Okay. The first one is 0, 1, 0. So to make that 0 turn into a 1, I'm going to need to put an inverter on there. Okay. 0, 1, 1. To make that 0 right there a 1, I'm going to have to put an inverter there. And a 1, 0, 1. Or 1, 0, 1, sorry. So I'm going to have to put an inverter there and an inverter on the last one. All right. Now I'm kind of too close. So what I'm going to do is I'm going to take this. Drag it down a little bit. I'm going to take this off to the side.
Space it out pretty good.
Yeah, because we're going to start putting a bunch of stuff in here, right? We'll be able to move it. All right, so I'm going to take a wire. I'm going to go from, this is my least significant bit. All right, so this is my most significant bit. I'm going to take it and I'm going to go straight out like this. The Q2. All right, so I'm going to put that on top. I'm going to put the next one there so that we can see A, B, and C. Okay. Yeah. Oops. Come on now. Like that. Thank you. That's still showing up pretty good. All right. A is not necessarily top, B is not necessarily top, but whatever you do, stay consistent. Okay? So I need an A tied to this, this, and this. Okay? So I will take this, go up to the A. Okay? I'll take this, go up to the A. I will take this one and go up to the A. But I've already got A connected there, so I'm pretty good. Okay? I want to go ahead and connect my inverters. All right. Now I want my B's going up to my B. Okay. So I'm going to take that B right there. I'm going to go out here so then I can get that's garbage. I won't have to go around this stupid. That's one thing that I wish I do. But I'm going to connect all my B's, right? To my B line. And then I'm going to connect all my C's to my C line. This one's going to be a pain in the tail. Yeah. Over here? Oh, right here? That's just extra length, right? Because I'm going to need to make a bunch of this. Okay. All right. So I need to connect all my C's. I need to connect this to C. All right. So now, if that number or that number or that number come on, C needs to come on. So I need to put a 3 input OR gate right here. To feed all those in. And that's going to give us our C and D, because remember, C and D both came on at the same time, right? All right, so let me. There was a way to label. I can't remember. We'll worry with that later. All right, so I've got C and D here, so I'm just going to tie this OR gate to C and D. So I'm going to go C, D, and connect. Yep. I just made a wire between the two, made a little loop of wire. I came down, I connected them like a U, just so it wouldn't confuse itself. Oh, I got you. Is that better? Okay. All right, we want to verify this real quick. We don't want to go on and then like have a whole bunch of like that 7-segment LED, like just having random things and trying to decode it right there, like figure out where we screwed up. So right now, C and D should be on. C and D should be on. On step 2, 3, and 5. Okay. So let's go ahead and run that. So whenever it hits 2, 3, and 5, 2, 3, 5. Yeah. So we're getting pieces of our puzzle right now. Okay. We're about to not. We only got 3 more circuits to build.
Now, is there a way, I think it was 2 weeks ago in class, where you talk about simplifying it down and breaking it down. Is there a way that you could do that with this or no?
Actually, I was gonna ask the same thing. You really need to work it.
Yeah, because like right now, like C and D, like if we didn't have it going through an OR gate, what would happen is if this was on and this was off, it would conflict, right? It wouldn't know what it needed to be. Okay. No, we can simplify this more. But some of these we can simplify more. But I want y'all to not get into the simplification mode of this. I want you to understand what's actually happening. Okay. We did simplify it a lot by taking that most significant bit out. Right. We'd need a whole lot more. We'd need 4 input AND gates. 4 input OR gate, and would have a bunch more wire going. Okay. All right, but we get 3 times that the B and C are on. Okay. All right, now E. When is E on? It's on for 0, 0, 1. Yes. All right. So let's go ahead and build that part. So we're going to stop this and instead of trying to crowd this 3 lines right here, what I'm going to do is I'm going to go down below this and I'm going to make me another bus. Okay. So I'm going to take my A. I'm going to go down here. I'm just making a long line so I can see which one's which. Okay. Got my A, B, and C. All right. Do what? No, like it gets pretty confusing if you don't, and sometimes they like you can't overlap them. You can run them across each other like we do right here. All right, I'm going to ask you something. I don't want it to get too confusing, but I think this might actually save you some time. Okay? That 001, it hasn't been used. Well, has it? E and G. All right, but what about that 010? We've already got that taken care of. All right, 010. on the D and the C, right? We've got that right here. Isn't that coming on at 010? I mean, yeah, 010. Yeah. Like, so we've already got a gate for that. Instead of rebuilding that, are y'all okay with us tying off of here down to that OR gate? Yeah. Like, instead of building another 010 or a 011, we got a 011 right here, don't we? Or 101 too. So with E, isn't it the same thing as C and D or a 001? Right? Everything else is the same other than the 001. Okay? So we could build 4 more gates, but 3 of them we've already got, right? I'm building them again. Now, it gets confusing if you don't see that. All right? So we've already got 010, 011, and 101 in the C and D column, don't we? So can't we just take that output of C and D and OR it with that 001? All right. So let's go here. All right. So we do not have 001. We've got to build that from scratch. So we'll take a 4 input or 3 input AND gate, and we'll put 2 inverters on it. 0, 0, and then we'll have a 1. We'll wire that up. We'll just go up to that C. We'll go over to that B. Okay, we're good there, right? That's a 0, 0, 1. So A is 0, B is 0, and C is 1. All right. Now, this circuit up here, this OR gate right here, takes care of all of these, right? So if we put a 2 input OR gate and we feed off of this line right here, we took care of all those jokers, didn't we? Right? And then now we've got this extra joker right here. And this will be our E. All right. Once you get that in, let's verify that that looks right. You got 2 input OR gate feeding off of this OR gate, which encapsulates all 3 of these numbers. Okay. So we'll turn that on. How's that? Something's been kind of funky. All right, so you see a piece of the R, a piece of the O, piece of the 2 B's. All right.
Question.
Yes, sir.
On, say we couldn't use one of those gates above, that's when not when someone comes on. Would you just run it from behind the wait. I guess my question is, what if
Like if we needed 2 of these, but not all 3, yes. Like, so we're about to peg off of this AND gate right here and this AND gate. Okay. But y'all see that we've got a piece of an R, piece of an O, piece of 2 B's. Are y'all starting to feel that like God mode come in where you're like, oh my God, I can do stuff other people can't. If you prefer not to use that term, I don't know, like titans of information, ice giants of knowledge. Now, I could redo all 3 of these circuits right here and put it into another, into a 4 input OR gate, right? But y'all can already see where that's just redundant. Okay. All right. So we're going to stop this now. We're going to go back and look at our F. When is our F on 011101? So we've got a gate for both of those, don't we? All right, so let's go find our 011 gate. Our 011 gate is this one right here, right? And we've got a 101 gate, which is this one right here, correct? So what if we just go grab a 2 input OR gate and we tied it right there, and that gives us our F, doesn't it? Now, might take a little extra time, but we're going to check that it's doing what we want it to do before we move on. All right, it's giving us more of our B's now, right? Now all we got to worry about is our G. Where's our G? We got a 001. We got a 010. We got a 011. We got a 101. So if it does everything that the E does, plus that 100, we don't have one of those. So if we just follow the E, right? Anytime the E is on, or a 101. Wait. Mm-hmm. Yeah, because we're making that hyphen. That's where the hyphen is. So that 100 is the only one that's not the same as the E, right? Right? I don't want to confuse you, but I mean, like doing it step by step, we kind of are getting it, correct? All right, so we need everything that the E does, which is this gate right here, right? Or we need it to come on at 100 also. So we'll take a 3 input OR AND gate, and we want it to come on at 100. So we need 2 inverters on the 00s, right? I want to move this down and over a little bit. Y'all know what I'm talking about when I say 1 0 0 is going to be A is 1, and then B is 0, and C is 0. Okay? So we're going to go from A. It's going to be a 1. So we don't need an inverter right there. We're going to go from B. This is 0, so we do need an inverter there. And then we're going to go from C. This is 0, so we need an inverter there too.
C is second.
So it's 1 0 0. Zoom in. Around there. So A is the top, B is the second, C is the third. We got A going to the top here. It's non-inverted because it's already a 1. We got B going to the middle. We've got an inverter there because it's going to be a 0. And then we've got C going to inverter because it's going to be a 0. Yeah, like, so since we're only using 3 bits, we're going to say the most significant is A, least significant is C. Okay. It'll always change depending on how many things you have. Like if we have 4 bits, then it'd be A, B, C, D, and we'd be dealing with a whole bunch of B, C, and D right now because A didn't even matter. Cool. All right, so for G, we got everything that's in E or this gate right here, right? Yep. So we're going to take an OR gate, 2 input OR gate, and it's going to be everything for E, which was, oh Lord, which one was it? This one right here, right? Right? It's tied to E. So we're going to take everything that was tied to E and or a 1 0 0, and that's going to be tied to G. Okay, so we simplified it some just through logic, right? We could go through and simplify it wholeheartedly, and that's kind of what I'm going to talk about for next like 20 minutes once we see this raw B, right? Go up here. That's it, bro. Yep. ROB hyphen B. ROB hyphen B. Sir? Is it doing it? Okay, so More than likely, okay, so the hyphen is also part of the R, right? All right, so let's see where we're at here.
Say it's going high.
All right, so
Or is it doing it right now? This thing going.
all right, so A, B, C. Okay, so right here, you've got A at the bottom. You got C at the top.
I thought A was the first one. The first one on the four up.
No, that's going to be C. So it'll be A, B, C. All right. So all you got to do is more than likely,
Just move the wires from top to bottom, bottom to top.
well, no, like because that's not going to change anything, right? Take this one and take this one. And then we're going to make this one the A. We're going to make this one the C. Okay. We're going to go from here over to here. And that's going to fit some of it. Okay. Because it looks like the first chunk of it. I'm really good at troubleshooting. Like, that's a rat's nest. He'll show you. Like, all you got to do is, like, take your top line and swap it with your bottom line.
Label gates, there's two gates not being out.
Not on here. Okay. Now, when we have to do a really big circuit, instead of having a ton of wires, we'll put them into a bus. Okay. And then we'll name each one of those wires like A, B, or C. And then, like, you know how we do in well, you're not in PLCs yet, but we can name something. And then instead of running a wire to it every time, we can just put a little tag on it and say it's that same name. And then logically they'll be connected. Okay. But the good thing is we can abstract things. Okay. So we'll build a counter. Okay, like we'll build a counter, and there's a bunch of ands, ors, and nots in it, and then we can abstract it and just have the inputs and outputs and make it something like this, where it's just a square box that represents a whole bunch of things that are going on inside of it. Okay, so like if it was important enough that they could say my name all the time, they could make a like right here we've got decoders, and we've got well, those are just binary to decimal, like what we built before where the LED was just going across. But on the output right here, like we've got a 7-segment output that is 1 hex digit, so we could put those 4 bits in and it would decode it and go to the LEDs like we wanted it to, right? So like let's look at this for a second. If if I put this hexadecimal, I'm not up there anymore. All right, so if I they've abstracted a binary to 7-segment decoder right here. Okay. If we hook that up, let's go ahead and add that. Go to output, and there's 7-segment display, and then 1 hex digit. Okay. All right, so that dot, I think, is representing our least significant digit, which would be C for us. So we're only going to count up to 7 with this, okay? So we're going to take our C and go to that top one. Then we're going to take our B and go, that little dot I think is representing your least significant bit, okay? And we're just going to work our way backwards. We're basically twisting those wires. We'll find out. If our numbers get funky, we'll know. Yes. So we're basically twisting those wires. Okay, I don't know exactly why that's not working. Do what? Maybe so. So instead of having it count up in binary over here, let me throw this on real quick. We'll put a high level here and see if it actually works for us. Logic level 1. Let's see if that works. Okay, so if I did a logic level 0 for the most significant bit, it would count out 0 through 7. All right, so let's change that to so let's take that logic level 1 out. Let's put a logic level 0, and it'll count the 7, 0 through 7. Okay. Okay. So on step 0, 1 ROB-B. Like they made a decoder that took it from binary representation to a 7-segment like 0 through F. Okay. We took it and we encoded that we wanted ROB-B, and then that dictated what our gates needed to be, right? And then we decoded it with those gates to get what we wanted out of it. The reason I didn't do a 0 through 7 or a 0 through F was because I didn't want you to feel like that 7-segment decoder or LED was anything magical, right? It's just LEDs in a certain arrangement that we can get certain things out of. All right. So I want you to have at least this. Under outputs and 7-segment display and 1 hex digit. Okay. This is what you're going to turn in for your lab. Okay. So I'm going to say ROB-B. Now, I want you to think even bigger. Okay. So I'm going to I'm not even going to give you homework this week. Okay? I just want you to read on decoders and encoders. We encoded information by deciding what those bits were going to represent, right? So we took an R and we said we wanted R to be represented by a 0001. Okay? So we did two things. We encoded and decoded. When we took our human readable stuff and we said that an R right here was going to be represented by 001, we encoded that data. Okay? And then when we said we want it to look like an R, we decoded it by making logic that would take that 001 and make it look like an R. Okay? Y'all follow? Now, how big of a step is it for my face? It's not. Okay? Now, we can represent stuff with like little, LEDs that look like straight lines, right? So we got a B there. Now, y'all trust me at this point, right? All right, so how would I represent my face? Okay, so we have like 8x8 matrices, right? That are 8 LEDs or 8 LED in a row, and then we've got 8 LEDs in a column, and we got 8 rows of that. So we got 64 LEDs, right? I don't want to draw that out, but I will draw a 4x4 matrix. Okay? Couldn't we get a little bit more resolute with a letter or a number with something like that? All right, now imagine that was, let's see if I can do this. So now I've got an 8. So I've got an 8x4 now. We've got a grid of 8x8 LEDs. That's exactly what's going on with your computer screen or that computer screen up there. They're just really small LEDs that are very close together. Right? And instead of just if the LED is on or off, we can encode data like how bright the LED is. Okay? So we could we could take this LED right here and we could call it a pixel. And that's what it is. With the monochromatic screens, we could just tell a pixel, which was a very small little square LED, if it needed to be on or off. Okay? Later on, we could tell it if it needed to be a certain level of on or off. Okay? So, like, we could have a bitmap. Okay? A .bmp, which is a picture, right? Just using pixel data. Okay? And a bitmap would be encoded, so you take a picture and then you would break it down into ones or zeros. Okay? All right. Now, at its easiest, we could tell if that pixel was on or off, you know, and we could encode it like this. So the first pixel would be on, the second pixel would be off, third pixel would be on, fourth pixel would be off, right? But that's just an on or off thing. We could say that for every 4 bits is going to represent a luminosity. Like, how bright is it? Okay, so now we're dealing with analog values being encoded into digital values, which are, you know, ones or zeros. But we could say that if it was off, it was 0, 0, 0, right? If it was half on, it'd be, you know, 0, 1, 1, 1. And if it was fully on, it would be 1, 1, 1, 1. So now we could have like a gradient. So would have like 15 steps from all the way on to all the way off, right? What would that look like? So the first 4 bits would represent the first pixel. Then the second 4 bits would represent the second pixel. So it's all the way on. Okay? Then the third 4 bits would represent how bright the third pixel was. So y'all could easily make a happy face with a 8x8, right? You could say this pixel needs to be on, this pixel needs to be on, this one needs to be on, this one needs to be on, this one needs to be on, this one, this one, this one, this one, this one. Right? And you could encode that by saying all of these are 0. So, like, if it's just on or off, so we'd have 0 for the first row, 0 for the second row, like we'd have 8 zeros, right? And then 8 zeros for the second row. And then we'd have like 0, 0, 1, 0, 0, 1, 0, 0. By God, are we not encoding a happy face? And then for the next one, it'd be all zeros. And then we'd have 1, 0, 0, 0, 0, 0, 0, 1. Are y'all start like, this is when I started getting excited. I'm like, oh my God, I can do anything. And then I'd have a 0, 1, 0, 0, 0, 0, 1, 0. And then have a 0, 0, 1, 1, 1, 1, 0, 0. And then I'd have nothing but zeros. Now, in the computer, it'd be just a string of zeros and ones, right? And if I just looked at it as one long thing, because it probably wasn't even squared up so that it looked like what I was trying to draw, it could be just one long line of stuff. And to decode it, I'd say every 8 bits is a line. Right? I'd say, hey, I encoded this so that I said for every 8 bits is a line. So take the first 8 bits, put it on the first line. Take the second 8 bits, put it on the second line. Take the third, boom, 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 boom. If I wanted to get fancy, I could have, 128 by 128. Squish them even closer together so I could get an even more resolute happy face, right? What is my screen resolution for my iPad? iPad Pro screen resolution. Uh, 2388 times 1668 at 264 pixels per inch. 264, and that's not even super high resolution. Like, what's 4K? What is 4K resolution? Mm-hmm. A resolution of approximate 4,000 pixels across, right? So it's 3840 by 2160. Now, what is a pixel? Up until this point, it's just, dealing with on or off. But how do we get a color? You can make any color out of 3 colors: red, blue, then tripped you up a little bit, and green. In reflective and subtractive color, like when we're painting, our 3 primary colors are red, yellow, and blue, right? Red, yellow, and blue in paint will make anything. Because when we're painting something, it's the reflection, or what gets absorbed and what gets reflected. When we're supplying light, so additive, it's red, blue, and green are our primaries. And between those 3 colors, when we're turning on a LED that's red and an LED that's blue and an LED that's green, we can make any color by mixing those 3 colors. Okay? So each pixel, we'll have like a green pixel, a red pixel, and a blue pixel right real close to each other. And that encompasses the pixel. You can see that, or if you like sneeze, and then you can see or if you look really close on your screen, like turn on something really white and get a magnifying glass or spit on it a little bit so you get magnification. And each one of, like, white is when red, green, and blue are all 3 on at the same time. Okay? Promise. And any variation of that is going to get you any color that you want. Okay? So now I might say my first 4 bits or my first pixel, whatever color, like whatever brightness that red part of it's going to be, my first pixel. Then my second 4 bits are going to be the level of my blue for my first pixel. Okay? And my third 4 bits are going to be the level for my first pixel. Okay. And then my fourth bit, or my fourth 4 bits are going to be my red data for my second pixel. So now you're starting to see that to get a picture, we're, doing a whole lot of data because we're only on the first part of our second pixel, right? So now we got 4 bits for that color, and we got 4 bits for this color. So now we're talking about 2 bits here. And let's say both of those are white, right? We've got 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, or 1, yeah, 4 ones representing 2 pixels. So that's 1, 2, 3, 1, 2, 3, 6, 12, 24. We got 24 bits to represent 2 pixels that are fully white. Okay? This is how bright the red component of it, the first pixel is, how bright the blue component of the first pixel is, how bright the green component of the first pixel is. So for just 2 little pixels, we've already got 4 times 6, 24 bits encoding that. Now, I don't know what order they put it in for different things, but you need to know what they use to encode it so that you can decode it, right? You need to know what you're decoding so that you know how to put it. Now, 4 bits is not very resolute. That's only 4 levels of color between super bright and off. That's only 15 levels. Like the old school Nintendos had 256, which was 8 bits, right? So it had 8 bits. So it had a better resolution. 512, 1024, like where are we at now? Right? Let's see. Let's look at resolutions. Color levels 4K. How many bits per color? See, that's what I'm telling you with paint. This is what I'm telling you with additive color when you're generating the color. Okay? Let's see, bit depth, 4K. So we know how many pixels we've got, but how 10-bit color range, which is over 1 billion total colors per pixel. All right, so when they used true color, that's 24 bits. When they used deep color, that's 30 bits. That's how many, like, how resolute it gets from brightness to darkness, right? If given enough pixels, you could recreate anything. Like, that's what they're doing right now. They're taking the reflection of the light off my face, encoding it into ones and zeros, and then that computer right there is decoding those ones and zeros back into light levels for each color. Okay? So, does that help understand how through encoding and decoding, we did a ROB, but if we had enough LEDs, we could encode my face and then decode it and it come out looking like it did whenever we put it in. Okay? Does that help any when we went from the 7 segment to like a 4x4, then to like a 8x8? And then if we just keep that, getting more dense, we can make a, more resolute happy face. I'd be, you could tell my beard was there. Y'all feel good? All right. So that's it for today. That one was long, which I can't help it, because I freaking love this subject.
This like lab.
Yeah, y'all have already done your labs. The deed part is your lab. I'm not doing anything but asking that you read over encoders and decoders again.
Or we just turn that picture over here